Hi, everyone. Ooh, wow, that's loud. Can you hear me? Cool. Great. I'm James Neeswand. I'm the CEO of Illyriad Games. I'm here on stage with Ben Adams, who's our CTO. It's fancy titles. We're a company of 6 people, so we can all be chief executives of something. We're a UK-based independent games maker. We're 8 years old. And we make massively multiplayer games. That's our focus. You may have seen some of the footage from our game Age of Ascent this morning in the keynote with Scott Hanselman flying it. Yep. Our first title was a fantasy strategy game called Illyriad. It's the perfect example of what not to name your company after your first title, because when you develop a second title, it makes no sense whatsoever. But this is Age of Ascent. You may have seen it this morning. Age of Ascent, it will be coming out later this year. It runs in the browser in WebGL in HTML5. It is a massively multiplayer game on a kind of a new scale of gaming. We call it an ultra MMO. This is just demonstrating the combat module. The full game will have exploration, trade and industry, mining, empire building, mission running, and all the rest of it. But this is the game running natively in the browser. This is footage taken from a playtest earlier this month. There was another one week on Saturday, if anyone wants to turn up. But that's quite a lot of players in a Twitch combat game. And this is only 80 players. Now, we have tested Age of Ascent up to 50,000 players in the same battle, in one battle zone, without sharding, without multiple universes, without separating space in any way whatsoever. And that's what we call an ultra MMO. It's a very, very large-scale game. So whilst the whole game can support maybe millions of players, in a single battle we can get at least 50,000, which is, we think, pretty cool. We write everything in HTML5 at the front end. We believe it should be playable anywhere, anytime, on any device. And we've stress-tested, as I say, up to 50,000 players. When we had 50,000 players in the same battle, the server was handling 267 million application messages a second. That's, I think, 23 trillion a day. That's quite extreme. Ben will be talking a lot more about the actual technology stack when we get to that, because fundamentally, he's the guy who knows things, which I'm certainly not. We have bit meetings once a month, again, to talk about the scale of we operate at. Our bit meetings are where we argue about who gets which bit in a message packet. Because in our world, 1 bit of data is 9 megaseconds of server bandwidth that's being consumed, because the number of messages going out is so high. So we've had to rewrite quite a lot of, I guess, settled technologies, almost treating TCP like UDP. And it's pretty extreme computing. You know, that's sort of the takeaway from my bit. It's not the only challenge of scale is the number of concurrent players. We also have to be able to, because we're a small company, to unfold space and fold it back in on demand. By which I mean, if say, for example, 2 alliances suddenly decide to go to war, over mining rights on an asteroid, or smack talk and chat, or whatever it is that sets them off. If they all undock and arrive in the same area of space, we need to very quickly spool up servers, unfold space, and handle the load without the whole system falling down. There are lots of ways of coping when you write an MMO with network latency. Spool up animations is a classic one. You know, when you click a button, it takes 15 seconds to cast a spell. That's a good way of synchronizing everything before the action. But we don't do that. We are just concentrating solely on real-time Twitch combat. The game hasn't even launched, but people are saying quite nice things about it. So this is just us showing off, I guess. Sorry about that. We also have one other, I guess, fairly obvious issue, is that our game will only run as fast as the slowest component. So it doesn't matter if we can handle 267 million application messages a second if we can only display 5 ships, for example. You have to have your rendering thread running at the same speed as your networking layers, the same speed as your server and your physics engine. It all has to run at the same speed. And that's quite a challenge. Luckily, there's lots of great technologies out there, and I think you probably had the introduction at the keynote from Scott Gu and Scott Hanselman about Service Fabric. That's one of the technologies that we're using. But there are solutions to these problems, and we have a technology stack that is pretty extreme. I'm going to run through it in 45 seconds, if you can imagine that, the whole tech stack.
Really?
So, here goes. You can do it in one breath usually. The overall architecture, we use Microsoft Azure for hyperscale on demand. Service Fabric orchestrates all of our clusters. Nano Server deploys new VMs for us. .NET Core is our high-performance open source framework that we use. At the server end, it's WebSockets for high-throughput bidirectional communications. Kestrel is the ASP.NET web server that Ben mostly wrote for Microsoft. ASP.NET Core is our pay-for-play, and the game engine and SQL Server. Sorry, I really can't keep up with this. I should slow it down one of these days. HTML5, so it runs everywhere in the client. WebGL for our GPU-accelerated graphics. Three.js is our 3D rendering library. TypeScript, you all know TypeScript, and Universal Web Platform, Windows Platform, because I gather all your Xboxes have become developer toolkits now. So that's pretty much it for me. I'm going to now hand over to Ben, who's going to go into a bit more of a technology in specific areas. And I don't know if there's going to be time at the end. If there is, we'll gladly take questions, or just come and grab us afterwards. We'll hang around, because we're happy to talk about anything and to go into a lot more detail. So I'll hand over to Ben. Thanks.
Hello? OK. So we wanted to create an ultra-massively multiplayer game. Human interaction and ingenuity drive our world, and it's about having no limits on that. We want unparalleled scale. The more human interaction that we can support, the bigger and the better our game is. We want players to sort of weave their own stories without artificial boundaries of world size, servers, play sessions, or matches. So to that end, we're creating a single contiguous universe, connecting everyone unshackled from location, platform, or device. What do you need to do? We started born in the cloud, but what does that mean? We need to think differently. Servers are a resource. They're not a feature. For example, we use Nano Server. Do we need Active Directory running on our Windows server? No, we don't. We want a dedicated service that we just spool up really fast, and that's one of the technologies that helps us get there. Every design choice we make, we want to fit in with that fault-tolerant, scalable system. We can't have the universe stop at any time. And to help that, you've got to think about componentizing all your separate systems into individually upgradable services, and that way decouple them from the underlying virtual machines and infrastructure. In our case, we use orchestration and balancing from Service Fabric. So hyperscale in Azure, that helps us handle unanticipated load handling in a cost-effective way. We don't know, as James mentioned earlier, suddenly two alliances are going to war. We can't predict when that's going to happen. We do know it will happen. And we scale up when it does happen really fast, but more importantly, we can scale back down afterwards. So we're only paying for the servers that we use. Equally, Service Fabric moves all our services onto the same nodes. It's not just one VM serving one job. Everything is piled in at a sort of high density. And then when they become hot nodes, we rapidly scale out, and the hot nodes are separated apart and distributed in a load-balanced way. One of the really important things it does is there's always this question about data. And, what system do you use to have your data? If you're scaling out your compute, you've still got that bottleneck in your data. If I'm using a SQL Server box, have I got one of them? What happens? Do I need a cluster of those? They're not very easy to scale up and scale down. Whereas your data living with your compute, it scales up as you scale out, and then you pull it back in when you're finished. More importantly, fault tolerance is exceptionally important. You want to keep a seamless user experience. Your users' time is precious, so you need to respect that. You don't want, your server falling down. In our game, you don't want to drop out of the game, wait 5 minutes to reconnect, find a match, do this. You want to go straight back in. Ideally, you don't even want to notice that the service has fallen down. You just want it to keep running, even no matter what's happening behind the scenes. So again, Service Fabric is something we use for this, and we use reliable collections. It's a programming model that's very understandable to most people that use .NET. There's the addition of transactions to operate across multiple collections. One thing you want to think about is quantize long-running tasks. What's that mean? If you have something that runs for 2 hours, you don't want to have it as something that runs 2 hours. You want to split it into discrete chunks so that it can be stopped and then moved across the nodes. As I said, if something gets hot, you've got like 5 things running on the same box and they're all using a lot of CPU. You want to be able to split them apart and move them to different nodes and then resume them and keep them running. So you want to embrace relocation. And again, Service Fabric handles this. So what's the sort of performance we get from that? So we're an empire-building game. We have economic price wars going on. It's real-time space-twitch combat. Commonly with MMOs, you press a button, you have a wind-up animation hiding your latency, and then an action happens, and you press another button. But this is Twitch. This is I press a button, I instantly shoot, and it's all about skill and targeting. So we have a universe that can support millions of players concurrently in it. And as we said, we tested 50,000 simultaneous players in the same spot in space, and rather than distributed around it. So if I have a little bit look at the architecture. So we have 32 microservices. We have routing services at the top, which they're the ones the players connect into, and they generally have a persistent connection in there. Although if one of those falls down, they'll just reconnect, find another one, and that handles the routing and hides the complexity behind the scenes to the end user, and that discovers where the other services are that it needs to communicate with. So the yellow one are the green ones are game functions. The purple are the routing, and the red is our hot physics engine that handles that high throughput of messages. And then we have some aggregate services that resolve around the whole data, which are our AI and our events. I can show you that in Visual Studio. Maybe. So here we have microservices. They exist as projects. They compile to an exe. We use .NET Core and ASP.NET Core. And then those are directly reflected into the services in the cluster. If I just show you in Service Fabric Explorer. So we have a 40-node cluster here, which is split across 5 fault domains and 5 upgrade domains. So when we're doing an upgrade, it upgrades them up through the upgrade domains, and the faults, the fault domains are separated into different racks across the server. So, if something took out a rack, it wouldn't take out any of those. And again, down here, as you may have seen this morning, there are that one-to-one relationship with the microservices there. So that's our setup. And just to finish, earlier today, Scott was playing Age of Ascent live on stage, and it was a live link. I was watching slightly in panic as I was watching the player count in the top of the board counting up as people from the internet were connecting in. I was a bit worried they might shoot Scott. But somebody sent me a picture, and I found one of those players. So this is Jeffrey Snover, it seems, was actually in there trying to hunt down Scott. So
Great.
that's all from us. Does anybody have any questions? Okay, so how do we
repeat the question? Yeah.
How do we combine the data that resides in SQL Server with the microservices? So the microservices are like our operational state. That is the current state of the system. Then we checkpoint periodically to SQL Server. SQL servers are historic and our analytical state. So we also use that to resolve over aggregate services if you would need to do sort of analysis and work out what's going on. But the microservices are the primary operational state, and then the SQL Server is sort of the secondary or subservient state, and also the history as it's gone through.
Yeah. The reason we split it like that is fundamentally is because SQL, Transact SQL is the only language I write, so we're not dumping it because Ben writes the rest of the game pretty much, so we keep it. But yeah, it's undocking and docking from space stations, deaths. When you kill someone or you're killed, that's when we'll go off to SQL Server. Then we bring it back in, I hand it off to Ben and the service fabric voodoo, and then everything else just happens magically. Does anyone else have a question? Yep. Sorry, I can't hear you.
It's continuous. It's driven by so it's completely event-driven by all the events coming in from the players and the thing. It's multi-threaded on the server. In order to support that scale, we can't say do this at this time.
It's one of those things of.
Yeah,
it has to be variable. Yeah, it's one of those things again about not focusing in on when you're in Service Fabric and you're in the cloud, you kind of have to not worry too much about keeping everything in sync because it's never going to happen.
But we operate with sort of integrated state between the so we integrate state between the next tick. When the next event comes in, we shift it on and integrate in order to work out how the world's changed for that.
Cool. Anyone else, or is that it? We'll be around afterwards if you want to talk to us anyway. So, yeah. Thank you very much.